Assalamualaikum. This is the continuation of part of video 3, clipper and clamper circuits. So this is part 2, clamper circuits. We have completed part 1, clipper circuits, in the previous video. So what is a clamper? A clamper is a network constructed of a diode parallel to a resistor and a capacitor connecting input to output. So now you can imagine that we are now going to introduce another component in our circuit, which is a capacitor. Okay, there you go. So network consisted of a diode parallel with a resistor and a capacitor connecting the input to the output. So this capacitor connects input to output terminal. Clamper circuits can be used to shape a waveform, just like as the clipper circuits. We are now handling circuits which is time varying in nature, and we want to see how we can shape the waveform that comes in to the circuit. So clamper circuits are used to shift an AC waveform up or down a DC value. So this is different from the clipper circuit. A clipper circuit clips. It eliminates certain portion, but here we do not clip anything. We're just shifting it up or down a certain value. So if I have, let's say, a square wave here, and it goes from positive peak voltage V to negative peak voltage negative V, so it goes in a complete cycle here from V to negative V up to T again. I can shift this square wave down. Instead of going from V to negative V, it goes from 0 to negative 2V using a clamper circuit. It's the same thing as well as for a sinusoidal input. If I have one sinusoidal input going from 0 to 20 volts, going to 0, coming down to negative 20 volts before it goes up to 0 volts again, okay, I can shift this. Instead of going from negative 20 to 20, I can shift it to go from negative 10 to 30. So clampers shift waveforms, okay, to a different DC level without changing the appearance of the applied signal. Nothing is clipped, nothing is eliminated, okay, it's just shifted. And in fact, additional shifts can be obtained by introducing a DC supply to the basic structure. You can add bias just like the clipper circuit. You can add bias to play around more with the circuit, with the values that you want. So again, what practical applications would use clampers? This is not covered in the syllabus as such, but it's always useful to know that what you're studying is useful in real life. So because clamper circuits can shift an AC waveform, it can be used to create what's called a pulsating DC waveform, one that doesn't cross the 0 volt reference. So let's say you get a signal that is going from 0 to positive down to negative. You can do a clamper circuit and then you shift it up all in the one direction value, which is what you call a pulsating DC waveform. It's pulsating, but it's not crossing the direction from positive to negative. Okay, so a common use of clamping circuits is to restore DC value to a signal. Sometimes when you have transmission of waves, okay, the feeding the resulting pulse waveform to a clamping circuit provides it with a well-determined DC component, a process named as DC restoration. Okay, so clamper circuits are also called a DC restorer, and these are usually mostly used in analog TVs previously. So a signal that has been transmitted through capacitively coupled circuit coming from somewhere, okay, would have caused the signal to lose its DC component as it arrives to another circuit. So when it arrives to the receiver, okay, now this receiver might have more circuits that operates in this direction here, but it would need a DC value to operate. Okay, so in order to do that, when you receive the AC signal, you can pass it through this clamper circuit, and you would have a signal with the DC restored without changing the waveform of the AC signal. That's going to be a pretty useful circuit. So operation, how does it do what it does? So clamping networks have a capacitor connected directly from input to output, as mentioned earlier, with a resistive element in parallel with the output signal. So the diode is also in parallel with the output signal, but may or may not have a series DC supply as an added element here. Okay, you may add added bias there. And the capacitor charges when diode is conducting and discharges when diode is non-conducting. Okay, this is one thing that you'll have to consider. It charges when diode is conducting and discharges when diode is non-conducting, and we need to consider this when we do our KVL later. So for our analysis, we assume the capacitor will charge up to its full value when the diode is conducting. Okay, when you do your KVL, we assume that it will be charged up to the full value that it is capable of. And the capacitor retains its charged value when the diode is non-conducting. I.e., we assume that RC time constant is sufficiently large to ensure that the voltage across the capacitor does not discharge significantly during the interval that the diode is non-conducting. So what's this all about? This is because our input signal is oscillating, positive, negative, positive, negative. So this capacitor will be charging and discharging and charging and discharging. So what it's saying is that when it charges, it will charge to the full amount, and when it discharges, it maintains that value that it has been fully charged to. And the diode orientation and presence of DC bias may change according to the circuit. We will alter the circuit, we'll modify the circuit based on what output we want and how we want to restore the Vin. Okay, general steps to consider for circuit analysis before we do examples. First, decide, again just like the clipper circuit, decide when the diode turns on or off by analyzing which portion of the input signal will forward bias the diode. Okay, so we have the circuit, we'll have to decide. So just looking at a quick circuit here, in the positive cycle it would forward bias the diode, so I can safely assume that the diode is on, is conducting when it's positive cycle, but when this alternating current Vin changes direction, diode will turn off. Okay, so when the diode is on, find V out. Find V out when the diode is on, and in order to do this, during the period that the diode is on state, assume that the capacitor will charge up instantaneously to a voltage level determined by the surrounding network. So you find V out and find the value Vc. Okay, so find V out and find the value Vc. V out is not that difficult really, because this is going to be a short circuit and voltage drop across this R, because R is in parallel with the short circuit, so V out is going to be 0 volts if there is no added bias here. Okay, and then we need to find Vc from KVL, and then find V out when the diode is off. Okay, so in this circuit here, the diode is off. Just now we had established that the diode is off in the negative cycle. Now when it is off, we assume that the capacitor holds on to its established voltage level when it has been fully charged, when the diode was on. Okay, so here we found the V. Previously we carried that value of V here, and then we find the Kirchhoff voltage law to find an expression for V out. And because we know that clamper circuit does not clip anything, is just shift, so check that the total swing from peak to peak of the output matches that of the input. So whether it is the output being shifted up or down, it doesn't matter, but the swing must maintain because the waveform is not changed. So check the swing of the output, it should be the same as the swing of the input. And then also throughout the analysis, maintain a continual awareness of the location, the polarity of V out to ensure the proper levels are obtained. It's just saying that make sure you know whether you're doing V in positive or V in negative. Now some of the textbooks that you look at, they change the notation of the voltage source, but my analysis here, I maintain the value of V in. Okay, I don't change V in with the notation going up positive or going down negative. I just maintain it, but I am aware of the value of the positive and negative of positive cycle or negative cycle. Okay, let's have a look at this example so that you understand what this whole general steps are saying. Okay, now let's have an example. Here we have an input signal which goes from 10 volts to negative 20 volts, and this is a square wave. Okay, now the clamper circuit, okay, I know it's a clamper because I see a capacitor, and this capacitor is connected from input to output. Okay, I also know that this is a clamper circuit because not only that there is a capacitor connecting input to output, output voltage is the voltage across the diode in parallel with the resistor. So this is a clamper circuit. Now first I have to decide when will it turn on and when will it turn off. Based on the orientation of this diode, it will turn on in the negative cycle. So the diode will conduct during the negative cycle and it will turn off in the positive cycle, because in the positive cycle the direction would oppose the positive direction of current flow of the diode. So in the negative cycle, so we're talking about this negative cycle first, diode will conduct during negative cycle, input negative cycle, and when it conducts, this diode is replaced with a short circuit. Okay, short circuit here, and when the diode conducts, VD is equals to 0 volts. I have also written here VC, okay, in the direction here of negative to positive. You can read in the text why the orientation here is negative positive, and this 5 volt added bias is also noted here. So please make sure that you get this direction of VC correct. Yeah. And when I do analysis on this circuit, when the diode is on, I know that V out is going to be equals to 5 volts, because V out is the voltage across this path, okay, which is 5 volts. So V out is equals to 5 volts. And when I do KVL around this loop, okay, around this loop which covers V in, VC and 5 volts, I will get negative V in minus VC plus 5 is equals to 0, which says that VC is equals to negative V in plus 5. Now, because this is a negative cycle, okay, I would have to consider the negative peak. Okay, negative peak here is negative 20. Okay, negative V in is negative 20. So, assuming that the capacitor charges to the full value, okay, which is the peak of negative 20, negative peak. So, VC is now negative of negative 20 plus 5, which gives me 25 volts. Okay, so VC is a value when the diode turns on, it is charged up to 25 volts, and when the diode turns on, which is during the input negative cycle, V out is going to be 5 volts. So I know in my output waveform V out versus T, when it is aligned, when this one is negative 20, my output is going to be 5 volts. Okay. Then we consider when the diode is off. When the diode is off, diode will be non-conducting during input positive cycle. So when the diode is off, ID is equals to 0. This one becomes an open circuit. Now VC, we already know 25 volts. Okay, and I'm going to carry that value as I do the analysis when the diode is non-conducting, which is 25 volts. So when I do a KVL around this loop, I'm going to get negative V in minus 25 plus V out, okay, is equals to 0. So V out is going to be equals to V in plus 25. Now what the reason we're doing this is because I want to find V out. Okay, I don't want to find V in because V in we know, 25 volts we know, 5 volts we know. We want to find V out, so the loop that we're taking is the wider loop here instead of this internal loop here. Okay, so we do a value here of V out is equals to V in plus 25. So at the positive peak, because this is a positive cycle, right? So we're considering the positive peak, which is V in equals to 10 volts. V out is going to be equals to 10 plus 25, which is equals to 35 volts. If I draw the plots aligned, okay, when it is negative 20, V out is 5 volts. When it is positive 10, which means that the diode is non-conducting, V out is 35 volts. So now checking the maximum swing as suggested in the general steps, 10 to negative 20 is 30 volts. So 35 to 5 volts is also 30 volts. There you go. Okay. So let's have another example. What happens if I have the same circuit, but now it's not an ideal diode, but I have a silicon diode with a forward voltage of 0.7 volts. So let's find waveform V out again. The same thing, except that now when I consider negative cycle, when the diode conducts, VD is no longer short circuit 0 volts, but it is 0.7 volts. And if I find V out, it's going to be -5 plus 0.7 plus V out, which is the yellow loop, is equal to 0. So V out is equals to 4.3 volts. Okay. And if I do KVL along this loop at the left, why are we doing this? Because we want to find the value that the capacitor will be charged to the fullest value, because when it's non-conducting, I need to carry that value of VC. So I get a negative V in minus VC plus V out equals to 0. So VC is negative V in plus 4.3. And at the negative peak, okay, V in is negative 20 volts. So assuming that C charges to a full value, VC is going to be equals to 24.3 volts and not 25 volts as in the previous example, because of this existence of the 0.7 forward voltage. Okay, so continuing, so the diode will be non-conducting during the input positive cycle. Okay, when it's in the input positive cycle, when it's open circuit, it's just open circuit, but the value of the capacitance here now has considered that 0.7 component, and now VC is 24.3 volts. So if I do a KVL around here to get the value of V out around this outer loop, I'm going to get negative V in minus 24.3 plus V out is equal to 0. So V out is now no longer 35 volts as it was previously, but 34.3 volts. And this is the value that we have. Instead of going from 5 to 35, it goes from 4.3 to 34.3, but the swing is maintained, which is from peak to peak value of 30 volts. Now, it not only works, clamper not only works with square wave, it can also work with sinusoidal input. So if I do this circuit here, if it goes from negative 20 to 20, the waveform is maintained as a sinusoidal wave. And if it shifts, it will shift from negative 10 to 30. So this would have a swing of peak to peak 40 volts. And this would also have a swing from 30 to negative 10, which is 40 volts peak to peak. So this is a variety of the clamping circuits. Okay, you can change the orientation of the diode. Okay, or you can add bias to it. And that bias that you add can be also changed in terms of orientation to have an effect onto the V out voltage that you have, whether you want to shift it down or up, or you want to shift it slightly higher or lower than what is intended. Alright, so read the text and do the tutorials for firm understanding on the subject matter of clipper and clamper circuits before we cover Zener diode regulator in the next video. Thank you very much. See you next video.